Okay, hello everyone. My name is Kyumin Kim of the KGSEA Math Circle, and today I will be presenting my open school presentation on the topic of Pacejka's magic formula and its usage in motorsport. And oh, and so to begin, you are probably wondering what is the magic formula? And so to understand the context behind this mathematical formula, you need some background on motorsports. And so in motorsports, the biggest unknown is how much grip the tires can produce when the driver turns the wheel, brakes, or accelerates. And so grip isn't constant, it is constantly changing. And so it depends on slip angle. And so therefore, the angle in which the tire is deviating away from the direction it is trying to go, the tire load, and so the total force that's being applied onto the tire, as well as the camber, meaning the angle of the tire that is uh, from the vertical of the normal vector of the surface, as well as extra factors such as pressure, temperature, and much more. And therefore, for lots of engineers, instead of guessing, Hans Pacejka developed a mathematical magic formula that takes measured tire test data and produces a curve that mimics real tire behavior. And so this formula allows engineers to predict how much lateral force a tire will give under different conditions. And therefore, the reason it being lateral force is that lateral force is the main force that allows the car to turn in the left or right directions. And so the core formula is as such. And so you can see it is F of y. And so the lateral force is equal to d times sine of c times arctangent of bx minus e of times bx minus arctangent of bx. And so a very lengthy and complex formula, but then we can kind of dissect it quite easily. And so first of all, f of y and x both respectively represent the lateral force as well as the slip angle in degrees. And so the graph on the right side here, you can see that is the example graph of the magic formula. And so some interesting characteristics is that near the 0 degrees of slip angle, and so between 0 and 2.5, we call it the linear region where steering response defines how direct the car feels. And so you can see that when the slip angle is increasing, even a slight increase in the angle results in an exponential increase in the uh, ten, turning force. And therefore, you can see that. And after that linear region, we have the peak region where the lateral force reaches its peak force output at around 3 to 5 degrees slip angle for racing tires. And then after 5 degrees of slip, the tire force starts to decrease, which results in tires starting to slide, the lateral force falling, and the car either understeers or oversteers, meaning that the car doesn't turn enough, or either the car turns too much and causes it to spin out. And so you might be wondering, what are the other variables and the parameters and what do they represent? And so a quick overview suggests that B is the stiffness variable. And so it represents the slope at the origin. And so it influences how quickly the force builds. And C is the shape variable, which kind of changes the width of the S-curve. And so how rounded the peak is. The variable D represents the peak or the maximum force level that the tire can produce. And E represents the curvature, which means it controls the drop off past the peak. And so how drastically the drop off point is. And so, yeah. And then to take a bit more detailed look at kind of how manipulating each variable changes the slope of the formula itself, we can see that D, like we said, it sets the maximum possible force. And so physically, it's about equal to mu times the force in the z direction, where mu is the coefficient of friction for the tire, and F of z is the normal load. And so you can think of D as the height of the grip curve. And so in motorsports, more downforce, meaning more normal load on the tire, results in higher D values, which results in more grip of the tire. And so Another key aspect is that the lateral force F of y rises with the normal force F of z, but the coefficient of friction typically decreases slightly as load increases. And so this characteristic is what limits the model from producing infinite amount of grip. And so this characteristic of the inverse relationship between F of z and the coefficient of friction is what allows the tire to have a drop-off point at a certain slip angle. And so you can see on the graph as the increases, the maximum force or the F of y in the y-axis increases as well. And so the next variable is C, and so the shape factor. And so C controls the width and sharpness of the curve. And so you can see that in our example, at low values of C, the orange curve, it is a bit more broader and has a flatter curve, and hence the force grows much more slowly. And at a higher C value, you can see that it is a much sharper and steeper curve where force builds quickly, but then levels off and has a sharper drop-off point. And so in plain terms, C changes how abruptly the tire reaches its peak grip. The third variable, B, or the stiffness factor, represents, so B basically sets the slope near the origin. And so you can see that for our previous slide here, going back, C also it has an impact on the initial buildup of the force at lower slip angles. However, for variable B, it's much more focused on the linear part of the graph. Hence, this drop-off point isn't really affected that much. And so you can see that at higher values of B, the tire feels very responsive to small steering changes, building up a lateral force much more quickly. And at lower values of B, the tire can is the it represents the tire feeling sluggish or lazy, in common terms, as the force builds up slowly and hence has a slower turn in force. And so engineers often call this cornering stiffness. And so uh, it basically, like it says, how stiff the car feels. And then our final variable, or E, is the curvature factor, where E fine-tunes the curve after the peak. And so if our previous variable D changed or varied the buildup of force, E does the opposite. It talks about the drop-off point of the force. And so with smaller E values, the tire holds more force past the peak. And so you can see that the orange curve has a much more smaller drop-off point. And with E that is closer to a 1 or value of 1, the force drops much more sharply after the tire exceeds its peak grip. And so this can result in either if the drop-off point is for the rear tires, that means the front tires have more grip, hence resulting in oversteer or the car turning too much. Or if the drop-off point is for the front tires, it means the car does not turn enough, resulting in understeer. And so this parameter makes the curve slope in the opposite direction, matching how real tires lose grip with a drop-off point. And so we took a look at all the variables and the definition of the formula itself. But then you might be wondering why this specific structure was made. And so why do we use sine, arc, tangent multiple times? And so a brief understanding of engineering mathematics is that although we do in engineering, engineers utilize core and concrete mathematical theorems and concepts, most of the actual useful formulas that we utilize come from intuition. And so Pacejka, the researcher, just played around with multiple different kinds of trigonometry in order to find a function that creates a graph or a slope that had matched his ideal shape. And so what was the factors for that ideal shape? Number one, it has to be linear at small slip angles, and it also has to saturate, and it saturates smoothly at the peak, and then it has to also be symmetric around zero. And so like you saw in our previous graphs, it is symmetric around the origin, and so on the right side, a positive steering angle meant a positive lateral force. The steering in the opposite meant a negative lateral force. And fourth, it must also be easily fit to the test data. And so like all the variables we covered, such as variable B, C, D, E, as well as the slip angles, they are all values that need to be first extracted from actual race data and actual real life data, and then feed it into the magic formula to have the ideal model for that specific tire. And so the nested sign of an arctangent does exactly this, where arctangent naturally flattens out at high values, and sine smooths the transition into a nice S shape. And then the variables B, C, D, and E adjust the steepness, height, and curvature to match real measurements. And so that's why engineers call it magic. It's not from first principles or other famous concrete mathematical theorems, but it still fits reality pretty well, and it's widely used within the motorsports area. And so how is this quote unquote magic formula utilized or applied in motorsports? And so advanced tire models that simulate how tires respond and behave are built up upon the magic formula. And so we don't just use the magic formula in and of itself, but we use it as a core pillar for bigger and more complex tire models. And so such models can be used to evaluate lap simulations. And so we can predict cornering speeds, braking distances, as well as general lap time, car setup. And so depending on how we simulate the tire to behave, we can change the car's suspension or the wheel camber, as well as the tire pressure to shape the BCDE curve, as well as for higher level motorsports where aerodynamics is a key component. We can also help out for aero balance, and so more downforce increases the and also shifts the optimal setup. And so depending on which tire, front or back, needs to be more balanced, we can change the aero balance for that. As well as kind of the biggest use for such tire models is control systems. And so not only in motorsports, but even in day-to-day life, normal cars, safety systems such as ABS or traction control, or sometimes even torque vectoring, all rely on simulated tire models in order to find the optimal range for performance. And so that will be all for my presentation today. I hope you guys learned something new, something more interesting. And so I'll be seeing you guys next time. Thank you.